Intermediate Algebra, Section 8.6. The graph of any quadratic function, f of x is equal to ax squared plus bx plus c, is a parabola. When you're graphing a quadratic equation, and it's in this particular form, which if we would multiply this out, we would end up with the quadratic function ax squared plus bx plus c that we've been looking at, we can pull off specific information about this parabola. And some of this may not make a lot of sense, but we're going to take a look at graphing some basic quadratic functions to tie this together. But the overview is looking at the components of this equation, determining the value of a if it is positive. If a is greater than 0, it determines which direction the parabola opens, and because in this instance, if a is greater than 0, positive, the parabola will open upward. If the parabola opens downward, it means that a was a negative or less than 0. The vertex is the turning point of the graph, referred to as the maximum or the minimum, depending which way the parabola is going. The coordinates of that vertex will be hk from this standard form, and the axis of symmetry, since a parabola is symmetric with respect to a line that goes through the center of it, that's referred to as the axis of symmetry. It is the equation x is equal to h. So as I said, some of this may be a little bit beyond where we're at right now, but we'll tie it together. And we're going to start with the most basic form of a quadratic function. F of x is equal to x squared. We're going to choose some values of x and then compute the f of x and then plot the ordered pairs. So if I set up a table here and choose some x values, plugging it in for f of x is equal to x squared, and then noting what our ordered pair is and recognizing f of x can be thought of as our y value. Let's try some values. If we put a -3 in here, we would have -3 squared, which is equal to 9. So we'll have the point -3, 9. If we let x equal a -2, we'd have -2 quantity squared, which is a 4. So we have a -2, 4. -1, -1 squared is going to be a +1. So we would have the point 1. Try it again. -1, 1. 0, 0 squared is 0. So we have the ordered pair 0, 0. Let's try some positive values. 1 squared is 1. Putting in a 2, we would have a 2 squared, which is 4. So we have the ordered pair 2, 4. And just to round this out, let's finish with a 3. 3 in our formula, 3 squared would result in a 9. So we have the ordered pair 3, 9. Plotting these points then, we have -3, 9, which is off the scale, 6, 7, 8, let's call it up there. We have -2, 4. We have -1, 1. We have 0, 1, 1, 2, 4, 3, and 9, which is kind of off the scale, and I didn't quite get that lined up there. A little better. Connecting those with a smooth line, what we end up with, whoops, cut my hand there. What we end up with is a shape that's known as a parabola. They're U-shaped and can open upward as this one or downward. Our turning point of the graph is called the vertex, and in this example, our vertex is at the origin. A parabola is symmetric with respect to a line that goes through the center of the parabola and the vertex. This line is known as the parabola's axis of symmetry, and it would be the line here that's going through the vertex. It's actually x is equal to 0, and if you notice, the point here that we had, -1, 1, reflected through the axis of symmetry gave us an equal point of 1, 1. Here we had the point -2, 4, and if we reflect that point through our axis of symmetry, we found it by calculating it, but using the reflective property, we could have found it just by reflecting as well. Well, what happens if we have the same equation, only we have a 1/2? What happens to our graph? So plugging in some values here, like we did in the last example, in our function, let's see what we get. -3, if we choose x to be a -3, we'd have -3 squared, which is 9, times 1/2 is giving us 9/2. -2 plugged in, -2 squared is 4, 4 times 1/2 is 2. Putting in a -1, -1 squared is 1, times 1/2 is 1/2. 0 will give us a 0. Putting in a 1, no different than the -1. Squaring it gives us 1, times 1/2 is 1/2. Putting in a 2, 2 squared is 4, times 1/2 is going to give us a 2 as well. And plugging in a 3, we'll end up with our 9/2, which is 4.5 for graphing purposes, might be easier. So plotting these points, how does this graph compare to just the 1x squared that we just got done graphing? We have -3, 4.5, -2, 2, -1.5. There's our vertex, or at the origin. 1, 1/2, 2, 2, and 3 at 4.5. Connecting those points, if you notice, our parabola is still opening upward. The vertex is still the same. Our axis of symmetry is still the y-axis because of the fact that we can reflect these points through that x equals 0 line, but it's wider because of the 1/2. It's taking a longer time for it to head towards positive infinity, having that 1/2. So what happens in this next example? Basically, we have the same form, only now we have a 2 as our coefficient. And just to do some quick test values again to plot this to help us see the comparison, if we put in a -3, -3 squared is 9, times 2 is 18. We put in a -2, which would be 4 times 2 is 8. A -1 squared is 1, times 2 is 2. 0 in is going to give us 0. 1 squared is 1, times 2 is 2. Putting in a 2 squared would be 4 times 2 is 8, and I'm going to skip the 3 because I'm clearly off my graph. I think we'll get a sense of what this is going to look like in comparison to what we just did. A -2, 8 is going to put us here. A -1 is at 2. We're at the origin. 1 at 2. 2 is at 8, which is just one beyond the graph that we have. Connecting these, we still have a parabola that is opening upward. Our vertex is still at the origin for this family form of this equation. Our axis of symmetry is still x is equal to 0, but in comparison, it is a narrowing compared to the 1/2 x that we had. And recognizing here was our x squared, the basic form, this is definitely narrower and headed out towards positive infinity much faster than plain x squared, and clearly this is wider, having that fractional value between 0 and 1 on the coefficient. One other example I want to take a look at this basic form of our quadratic equation with something times x squared is the following. And plugging in some values again on this equation, our x and our f of x. If we let x equal -3 squared is 9 times the -1/2 is going to give us a -9/2 or -4.5. Putting in a -2, squaring it is positive, but timesing it by a negative will give us a -2. A -1 squared is 1 times -1/2 is -1/2. 0 results in 0. 1 will be a -1/2 because the 1 squared is 1 times a -1/2. Putting in a -2, squared is 4, but timesing it by a -1/2 is a -2, and we could go on. But to plot this, -3, -4.5 is going to put us here. The ordered pair, -2, -2. The origin, I guess I skipped over my 1, -1, 1/2. +1, -1/2. I meant this to be a +2, plugged in gives us a -2. So +2, -2, and if we put a 3 in, we'll end up here at -4/2, or through reflection. Connecting those points, almost caught the points. We have, different than our last parabolas, this is a parabola that is opening downward. It's a reflection of the y equals, or f of x is equal to 1/2 x squared. It's exactly the same, only it's opening downward instead of up. And it has kind of this pancake effect to it, that it's a wider parabola because of having that fractional coefficient on our x squared term.